Hey, so welcome back, everyone. So hopefully everyone turned in the homework, and for those, maybe other people will show up a little bit later after getting getting everything taken care of. The good news is the next homework is not due till April 13th, so that's like 2 or 3 weeks, and the next homework is worth 100 points again. The last one was only worth half the points, but it hopefully should be, so it shouldn't take as long. So I'll be on the stuff in regression, and this is the last lecture on regression, although the one on Monday we'll talk about cross-validation, which will be related to the stuff in the homework as well. So it's going to be doing stuff. I've set it up so it's really easy to do stuff in MATLAB. If you haven't used MATLAB before, it's pretty easy to use, and I've kind of told you most of the very basic commands and tried to set stuff up for you, so it's not too hard to do. And it's basically just kind of walking through and seeing how this stuff works. I got your project intermediate reports. I haven't gone through all of them yet, but hopefully within the next week or so, I'll get some useful feedback on that. Homework 3 grades. There's a little delay in that. Those should be posted shortly as well. And the quizzes probably tonight, maybe. I'll post the grades for those. Okay. So the topic of class today is going to be regularized regression. And in particular, we're going to be talking about mainly focus on a technique called the lasso. So the lasso, actually the lasso is not a technique. It's kind of a problem setup. It's kind of, as opposed to ordinary least squares, you would use the lasso, but there may be more than one way to solve this setup. And so I'm not totally sure where the name the lasso comes from, but that's what it seems to be called. So if you remember, the regular setup for regression is you have some data set P, and it's a bunch. You can think of it as a point set in RD plus 1, but it's special. The dth dimension is special. So typically we look at pictures of data that lies in 2D, right? And so then there are 2 coordinates now. There's the x coordinate, and then there's the y coordinate. And the y coordinate is special. You want to try and model or predict the y coordinate based on the knowledge of the x coordinate. Okay, so typically we say we want to fit some line through the data. So then how this works is then if I'm given a value in the x coordinate, this is my guess of the value in the y coordinate. Okay, and so, but in general, you may not say just in 2D, you'd say that this is actually in some d-dimensional space. So your input now are these d coordinates, and you want to predict just one y coordinate here. So this is always R1. There are some generalizations where you can predict something in higher dimensions as well, but typically you just want to predict this one value. So then kind of the standard thing we talked about is finding this red line through here, and we can think of this line, we'll call this A. And so then the way to model this is you break this P into 2 parts. You have Px and Py, and again, this was in d dimensions, and this one's in and this one's in 1 dimension. So if you think of this as a matrix of data, so then you have, maybe you have n coordinates here, and you have d plus 1. And so you can break this into two parts. The first part here is going to be, this part is x, and then this other part, this last dimension here, is going to be y. Okay, and so now in order to, or we'll call this, in my notation, right, this will be px and this will be py. And so then in order to solve it, we're actually going to map it into another matrix, X, and this is going to be, again, d plus 1 dimensions, and this will again be n values here. And again, you're going to have the same part. This is px here, but then this last column is going to be all 1s. Okay, so this will be a matrix X, which is going to be n by d plus 1. And then we'll also have this vector py. Okay, and then this line A here, we're going to think of this as a vector. So then you're going to get as input, essentially, the input for a prediction. If this is some, let's do this in red here, right? So if this is some input data point P here, this lies in RD, but I've made it up to RD plus 1, and so P is equal to P1, P2, up to PD, and then maybe I'll call P0 at the end. And this coordinate is always 1 right here. But these other are the input, and what I want to do is predict this value here. This will be yp hat, and that's just this y value here. And so we're going to say that, let's go over here, that yp hat is, we want to write this as A. So we're going to say this is going to be the sum over I equals 0 to d of pi times ai. Right? So A is now going to be a vector a0, a1, up to ad, and I need to find this vector that tries to get this y hat, and what I want is that y minus the true value of py minus yp hat is small. And in fact, so I want this to be small for all of the input data points. And so the goal is going to be the sum over all p in my data set, such that py minus y hat of p, so that this difference here, so these are two values, squared is small. And so this was the least squares estimate. Okay, and so there was this Gauss-Markov theorem that we talked about, where it said that in order to get A, the optimal way of doing this, where you had min of A of x, you can write this as xa minus py2. So if you want to minimize this, now this is a vector, an n-dimensional vector. If you want to minimize this over A, then the optimal way of doing this was going to be x transpose x minus 1 times x times py. Okay, you could write this out in this notation, and if so, under two conditions. So if you wanted an estimate that was unbiased, and there's no known correlation in the data, then this is the optimal way of doing this. Then this is going to minimize this error score. This is the minimum solution for A. This is the best fit line here. So this line is described by these these d+1 values, and it's kind of for any point you can get this prediction. Yeah.
Is the third X transpose?
Yes. Yeah, it should be transpose. Thanks. Yeah. So this should be transpose. Yeah. So there was this optimal way of doing this, and if it was unbiased, then there's no correlation. And it assumed. So this model works is it assumes that there's noise in the data, but it's this vertical noise off of the line. So for every data point, to get the blue point, you are essentially given the x coordinates exactly, and then to get the y coordinates, you projected them onto whatever the optimal line was, and then you added some unbiased noise. And each of the noises was independent. And that's kind of the model this is working under. So if it's, what we're going to talk about today and what the lasso solves is it's going to look at this assumption that's unbiased solution. Unbiased means that if I took any of these values and I looked at any of the blue data points, say this one, and I looked at the expected error without knowing which data point I picked, that the expected error, the expected distance from here is going to be 0. Sometimes it's above, sometimes it's less. Or the expected squared distance is going to be 0. So if that's the unbiased solution. But if I were to try and predict new data, and there's a formal way of kind of quantifying this with cross-validation where you said I trained on a subset of my data and then I wanted to predict how well it's going to do on the other parts that I randomly left out, and I want to do better on those, then I can actually give a better error on average if I allow some bias in the solution. And this lasso is going to give this biased solution. Okay, so let me write this down. So the lasso. Is defined. So it'll give you an A hat, which is the arg min over all these values A that we're trying to find. And this is our best fit line through here, where you want to minimize x times A minus py, which is the same as before. But you also want to minimize, you want to make this expression a bit more complicated, where I also look at this vector, and I have some value here, and so this is called the regularization parameter. So I want to say, for some value s, I want to minimize this expression. I'll call this a hat s. Right? So I'm putting this extra term, so I'm not just minimizing the least squares. So this 2 norm is, you can write this as squared there sometimes, but if you don't just want to minimize the least squares here, but you also want to say that I want to have an extra term which is a penalty. And this penalty is saying that if A is really big, if the coefficients are really big, then that's bad. Okay? So if the coefficients are big, that's bad. Why would that make sense?
You kind of want to force a sparsity to it.
Yeah, okay. So yeah, okay. So we talked about on Monday. So one of the main things is sparsity. So sparsity would mean that I'm solving for these values A, but if I go back to this expression here, it's the sum of all these terms of pi times ai. What I want is, so sparsity in this context would mean that some ai are equal to 0 exactly. So that means when I make the prediction and I have a bunch of coordinates for x, I don't need to look at some of them. Some of those coordinates I can just ignore. I'm gonna, to get the prediction, I multiply them by 0, so it doesn't matter what they are. So that would be the sparsity thing here. And so, but if I wanted to do sparsity, so I might instead use a different norm, the A0. Okay, if you remember what the A1 norm is, the A0 norm what is going to be something like is going to be there's different ways of writing this, but the sum over I of this function where it's 1 if AI is not equal to 0 and 0 if AI is equal to 0. Right? So if it's 0, if it's not 0, I get a penalty. If it's 0, I don't get a penalty. So it's saying I just count the number of non-zeros, and I have more penalty the more non-zeros I have. So people would like to minimize this A0 norm. But this turns out to be a very hard combinatorial problem, lots of local minimum, and I don't remember if it's NP hard to solve or if it's just in general kind of if it's not known how hard it is. But this one version, if you remember the A1 norm here, this is equal to the sum over I of the absolute value of the ith coordinate. So I just want to sum the values of these. I just want to sum the values of the coordinates. I want these all to be small. So of course, if it's 0, it's as small as it can get, which is great, right? But if it's 0.0001, I still have to pay attention to it, but it's not 0, but the cost is not very small. It turns out, and I'll kind of explain this through some pictures, that by trying to minimize this one norm of this coefficients, it actually snaps a lot of these exactly to 0. And there's kind of some neat reason why that works. Okay, so this formulation is called the lasso. So this is a problem setup. If instead, and we had mentioned this in the first lecture on regression a few weeks ago, if instead I use the A2 norm, and remember this is AI squared square root, right? If I use the 2 norm here instead, then this is not going to bias towards, this is still going to bias the solution, and this actually still gives some enhancement because of the bias as well, but it's not going to get sparsity. This is called, so Tikin in NOV, I'm probably spelling that wrong, regularization, or if that's hard to say or spell, then you just call it ridge regression. And so this one is nice in that it actually has a closed form. In this case, we'll call this A hat S. Is the solution to this one is going to be X, what is it, X transpose X plus S squared inverse X transpose PY. So I can solve this one exactly, so this version of ridge regression, but this is not going to get me sparsity, and we'll see that in a bit. But it still does have another advantage. So one of the advantages is sparsity. There's another kind of reason why people still do this ridge regression instead of just the regular or ordinary least squares. What would be another reason to do why, maybe an explanation of why this bias might help? So who's heard of regression to the mean? So has anyone heard this concept before? Do you have anyone care to try and give an explanation of it?
That over time we tend to go to the mean, like for the continuous experimentation where there's randomness, we always over time we tend to so if you were widely successful,
yeah,
that, like just by picking a lottery, eventually you will be losing also, so that your average is whatever the expectation is.
Yeah. So if you're very successful early, maybe you're going to be more average later in life. You know. Any other thing you add to that? So So there's there's kind of some, this is kind of a confusing concept, and it doesn't always click with people. So there's an example. Let me try and go through. So let's say that I gave everyone in this class a test, okay, and the test was a true, false test, and so it's going to have two types of questions on it. Half the questions are going to be easy, and so hopefully everyone would get 100% on these. Okay, so let's say everyone gets 100% on the half, but the other half of the cues are basically random, so that no one has any idea. So everyone guesses. So everyone guess, and this gets a 50%, right? So what is the average score going to be? The mean score. The mean score of the class, hopefully, would be 75%. Because people would get 50% right 100% of the time, and the other 50%, they'll get those right half the time. Right? But if you look at a class, because of if everyone guesses, then what you're going to get is some sort of distribution. So something like this, where this is 75%, and maybe if there are enough questions, 50% is way out here, and 100% is way out here. But there's going to be some people in class who are doing very good. These people did really well on the first quiz and got greater than, say, 80%. Write this a little better. So greater than 80% on the first quiz, right? So there's some fraction of class which is going to wind up here. Okay, so then let's say I took just these people. I said, okay, all of these people passed. I was very mean, and only these people got to take had to take the test, in the second half of the class. Actually, I'm going to switch this around to be a little bit nicer. Let's change this example on the fly here. So let's say these fraction of class who got less than 70%. And I'm going to say these people had to retake the test. Okay, but I gave exactly just as hard a test again. The first half was easy. The second half was random. Okay? So what do you think the expected value of this part of the class would be? If I retook the test, what is the expected score? Right? The score is still, expected score is still going to be 75%. These people are going to regress towards the mean on the second part, right? So they're going to, on average, still do the same thing because the first part test was independent of the second test. So if we don't know there's some dependency here, then you're probably going to look like the mean afterwards. Okay, so in real life, there often is some dependency, but there's also some parts which is independent, right? In all sorts of phenomena. And the part that's independent that part is going to tend to look like the mean. If you were very lucky or had really bad luck early in life, then you're going to have average luck later in life. Unfortunately, it doesn't mean that you're going to have better luck later in life. There's, I don't know, maybe some people believe in karma and all that. But the karma will only get you, back where everyone else is in the future, not any better than that. But on average, you're gonna probably do better. You're probably gonna get closer to you'd expect to do closer to the mean on the next time. Now, in a real class, there's actually distribution in skill levels, and so some people will do better the first time, will probably also do better the second time, but they may not do as well as they did the first time. And that not as well is a regression towards the mean. The part they got lucky on before, they may not get lucky on again. Okay, but this is with just a single value so this idea of regression to the mean was just a single value on a quiz. But we want to do this for actually like this linear regression instead. Okay, so we want to do this for linear regression. And so so this isn't going to be kind of a formal analysis of it, but we're going to think about it as, let's say that data looked like this, and it happened to be that the average score, the average value here was 0. So we don't have to worry about the term that's the offset. It's a little bit more confusing to think about. Okay, but we have this, so we don't have to worry about the offset score. So the prediction line is going to go through the origin. Okay, so maybe the best fit line looks like this, goes through the origin, is like here. So if I were to regress to the mean, what would this mean in some sense? How would I want to go back to something that was kind of average? So I want to look at just not, so what this is doing is essentially saying that the data points which are over here are greater than 0 tend to also have a value greater than 0, and the ones less than 0 tend to be less than 0. But overall, if I look at an average point, its value is going to be exactly at 0. So I kind of want to bias every prediction I have towards 0, and what that means, that biasing of the prediction is going to make my slope smaller. If I predict it's closer to 0, then I want the slope to be smaller. Okay, so let's draw another picture of this, or let me just finish up this thought here. Okay, so another way of thinking about this is that if I have data, so what I might have is some data that looks kind of like this. It's going happily along, but then I have one data point all the way up here. Right? This one data point up here is going to cause my fit maybe to look like this. It's going to be my slope's going to be very high because of an outlier point. Now, for this to make sense, we have to remember that we assume that the x-coordinates of everything are given to us, are not in any dispute here. But the y-coordinates have some noise. So this y-coordinate, if it's an outlier, it's going to be very far from 0. It could be, we could have these points really far away. And we want to say, well, I want to bias away from the outliers. If the bias is, if it's affected the slope, then I kind of want to make the slope smaller. And so a better plot would be through here and kind of would ignore this point here. Right? And so doing this, so this is a little confusing. A lot of the pictures you see of outliers will actually draw it down here because it fits in space. And when I drew this picture, like I had to go up into this other region to draw this. So a lot of the outliers will be down here. But it could be that the outlier is also so far down this way that it caused the slope to be negative. And then again, it goes back to 0. So this is kind of another way of thinking of why this might work. This first explanation in that the average population is 0, so you want to bias the slope that way, is actually closer to the formal way of thinking about it. But if you have these very large positive outliers, it's really often infinity, like you typed in an extra 100 zeros when you're typing something into Excel, like you held if you ever type something in, you hold the number pad down or something, you get these data points which are way, way out of there. And they're going to totally control the slope. And even if it was really far negative, then it would have caused the predicted slope to be negative too far. And then just predicting everything at 0 would have been better than any sort of negative slope that you had before. Right? So this is kind of the idea. I want to bias the slope to be a little bit smaller. And by doing this, I'm saying I'm penalizing any of the coordinates for being too large. So I'm saying if they're too large, then I'm going to penalize these coordinates. Okay, so I didn't talk about this parameter s. Okay, so before the least squares, I didn't have this s parameter. So now I have to deal with this extra parameter s. So how should I? What can I do about that? What should I do? Should I just? Is there like? Do you think there's gonna be a magical number? I should always pick like 1/2, or I should kind of guess. Throw some random numbers up there, see what happens. So it turns out, what you want to do, and there'll be most of the lecture next Monday will be on cross-validation, but you somehow want to do cross-validation to pick this. And what that means is that to do this training, if you go back to this picture, you have this data set X, and what you're going to do is you're going to say, well, I'm going to keep some of this data out. So this is going to be, say, my testing data, and then the part up here is going to be the training data. And so I'm going to just take this part here and have this go down into X, and then I'm going to have this leftover data. And I'm going to use this leftover data to say, based on how well I did on this leftover data, which value of S worked the best. Okay, and so that's, you're going to break up your data into two parts and then use the leftover data to pick the best value of S. And I'll just say a little bit about more of what place, at what step do you want to do that. Yeah.
So like the test data, you choose maybe like a small subset, so you can make like absolute calculations on it?
Yeah, right. So, anyways, once you get this value AS, you can calculate, it's very easy to calculate the error. You have the values Y associated with it, and you can, pump it into this formula and get these values Y hat for all those. So, it can, sometimes you want to do like 10% of your data, maybe 1/3 of your data to be used for cross-validation. So in this case, we just want to pick one parameter, but there's some settings where you want to pick more than one parameter in the model that you're doing. And so in those cases, you may need a fair amount of data to choose the best value there. And there are other ways where you do this multiple times, but you only leave out one data point, but you repeat it with leaving out different data points at a time. And so there are different ways of doing this cross-validation. But this is a very important thing. Otherwise, if you're building your best guess of this parameter S on your actual data, so if you test it on the same data that you trained on, the best value of S is always going to be 0, right? Which, maybe if you don't believe any of this regularization garbage, you think, of course the best value is going to be 0. Why do you add this extra term here? It turns out if you actually do cross-validation, there's going to be some value of S which is going to do better than 0. Unless the data actually fits perfectly on a line. So unless the data fits perfectly on a line, then there's some value of S which is going to do better than 0. And so you want to figure out what this value is. Okay, but still it seems you need to check a lot of values S, and this is kind of tricky. Okay, so let's talk about, let's see, before I talk about why sparsity works, how would you solve this? If it's ridge regression, there's this magical way that you can use this kind of the same matrix inverse as you did before to solve it exactly. But for the lasso, it's trickier. Yep.
So I'm in a different class than this, but we do things a lot like this. You can kind of represent it as like a functional solution, like a functional integral, and then do Euler-Lagrange and then try to come up with a value on S.
Oh, so you're trying to solve for the best S.
Yeah.
Yeah. So, but I'm asking maybe a simpler question.
Okay.
So, say I'm given S for one particular S. How do I solve for a hat of S? How do I find the fit to that? So I guess you know, if I know how to solve for a hat of s for any value s, I can try a bunch of values s. You know, just a very, very basic approach. Try a bunch of values and then do cross-validation, see which one works the best. And, you know, that's one reasonable way. But I need to be able to solve for this a hat of s. And I can do that here in the ridge regression with this closed form solution. But it's not as clear how to do that for the lasso. Because of this L1 term here, it doesn't cleanly decompose. Okay, so we actually saw a way how to do this already. So you can use lasso plus orthogonal matching pursuit. So we can pick one coordinate at a time. And so I'll just quickly refresh why this works, because this is not going to be the best way of doing this, but it'll help. It's a little tricky to see the best way, and this will kind of build up the intuition. And just to review orthogonal matching pursuit again. But the idea is you're going to set, you're going to build up these residuals and try and make these as small. And initially, this is py. And initially, you're going to say aj is equal to 0 for all values j. So you set all the coordinates to 0. And then what you're going to do is for, say, for I equals, say, 1 to some t, where maybe you'll stop when you get t coordinates. Okay? Probably don't want to use t here. Let's see why. So 1 up to m. So when you stop when you get m coordinates, then you do this process where you pick the best row. This row is arg max of xj, which is a row. Sorry, this is a column of x. The best column of x. So this is where the dot product with the residual is maximized. So I'm going to maximize the column of x. So the one dimension. So this is picking the one dimension, which is explaining the most about my data. Okay, and then I'm going to set aj equals to the arg min. And so I can solve this dot product, right? I can just check all of the values. I can solve this for some value gamma, where it's r minus xj times gamma squared plus s times gamma. Right? So now what I'm doing, instead of solving this least squares solution, I can solve this L1 solution. I've added just the size of gamma here. So I want to penalize just the term gamma, this coordinate here. And so this I can solve now, even though this looks like the same equation as before, but now this is just a single value, right? This is in R1, right? So this is a single value, and this actually turns out to be a convex equation, and you can solve it by, you can actually, it looks, you know, it's going to look like a function, and it's going to be piecewise, I guess this is piecewise polynomial, but it's going to be convex. So I can look at all these points where each data point is either getting increasing or decreasing as I'm changing this gamma value, and there's going to be some point where it's minimized. And I can solve each of these pieces. So you can solve this explicitly. So if you're careful about it. So if you wrote this down and looked at the function, it's going to be a piecewise. This is going to be piecewise quadratic, and it's going to be convex. So you can solve for this value gamma, which minimizes the value aj. Right? And once you have this aj, this gives you the jth coordinate. Right? So now I need to reset this residual. So where I've subtracted out the effect that I learned from setting the jth coordinate here. And I just set one coordinate at a time. And I set each coordinate based on which one tells me the most about the data. And then when I finish with m of them, or the residual is small enough, I stop. Okay, so this is not going to give me the optimal solution, but this works reasonably well. This will give you a fairly good solution, and it's not too hard to actually implement this. So I probably could ask you to do this. I think I'm not going to ask you to implement this, but I could ask you to implement this, and you should be able to do this. This step is a little tricky here, but you know, you could figure it out. Okay, and then you know, just return A. So you can do orthogonal matching pursuit, just pick one coordinate at a time, and you're picking them in a greedy way. And this gives you a reasonable answer. Right. A1 up to A d plus 1. Right. Okay, so this is one way to do it, but this solves it for one value S, and this does not give you the optimal solution. So I'll build on this next and show you how to get the optimal solution and actually how to get the best value S as well. And this will use a technique called least angle regression. Okay. But before I do that, to kind of figure out why this works, why this least angle regression works, I also need to explain the sparsity part of this. Okay, and this is maybe the coolest part here. Okay, so again, my goal is to write up. So I want to find this AS, which is the arg min of A of x A minus, I'll just call this Y, plus this S times the one norm of A. So this is the lasso. So it turns out that there's an equivalent formulation where I can say find a T, which is the arg min of A of x A minus Y, such that the one norm of A, let's look like this, is less than or equal to some value T. Okay, so this is different. This one is saying I just gave you some function and I said just minimize this function. This one says now I'm just going to ask you to minimize this least squares problem, right? You can minimize the least squares problem if you want to, but I'm going to restrict that the sum of all the coordinates in A are less than or equal to some parameter T. Okay? It turns out these two are equivalent, meaning for every value of S, the solution AS, so there's this property for all S in R1, then there exists a T such that AS equals AT. Right? So for every value S, there exists another parameter T that gives me the exact same solution. Okay? So to see why this is true, so what I can do is I can set this parameter. Let's see. I solve for AS. Okay, and then I set. If I solve for AS and then I set T equal to the one norm of A. So it turns out that'll always give the. Is that right? That'll always give the same solution. Yeah, so you can set T equals to AS. Okay, so the reason for this kind of this dual form is that this one is much easier to understand what's going on. This is much easier to conceptualize and to kind of understand from the point of view of an algorithm. So the least angle regression is going to solve this for all values T. It's going to give the solution for every single value T. And then that means there's the value t, which gives the best solution, corresponds with some value s. It turns out the value s or the value t doesn't matter. All that matters is the output that gives the best solution. Okay, so this means as s is increasing, there's more penalty. That means I'm restricting the size of t to be smaller. So as s increases, t is going to decrease, and as t increases, s is going to decrease. Okay, so at this point, it's helpful to draw kind of a picture of what's going on here. So let's see if I can draw this well. So we'll draw this picture in two. Well, so this will be kind of the three-dimensional problem. But I'm going to draw. So x is now going to be a subset of R2, and so that means that the A we're going to solve for in this picture is going to need to have two dimensions to it. So they could be the slope and the intercept. Or maybe if that's confusing, assume that I fix the intercept to go through 0 and then the two parameters of the slope. Okay, and so if I set this relationship is also true if I do the 2 norm instead of the 1 norm, so I can do the ridge regression instead. But let's say that that a hat is right here. So this is the solution. This is the least squares solution. Okay, and so by putting so now to understand this, I'm going to draw. So A now, I want the bias to be small. I want the coordinates to be small. And what this restriction does is it's saying it must be within a ball of size t, but it's a 1 norm ball. So that means that there's some value t here on these different coordinates, minus t, and the 1 norm ball looks like this diamond, right? And I can also draw the ball for if I was doing ridge regression instead. It's going to look like a standard, well, it's supposed to be standard ball. It's really hard to draw circles on this thing. All right. That's reasonably good. Well, that's supposed to be a circle. Okay, so this is, this ball represents A2 less than T, and the blue one is going to be the 1 norm is less than or equal to T. Okay? So I'm either restricting the solution to be within this blue ball or the red ball. The red ball is ridge regression, the blue ball is the lasso. So my solution is restricted to be in here. I'm biasing the slope to be small. But then the least squares solution was out here. So I want to minimize the distance. I want to minimize the error, the extra error from the least squares solution. It turns out there's going to be some part which is projected, lifting off the plane, and some part which is inside the plane. And so now the closest point is going to be, I'm minimizing the L2 distance up here. This is a 2 norm. That means there's a ball around a hat for the best solution, which is a 2-dimensional ball. And let's see if I can draw these well. But this ball represents, right here, this is the solution for this is the solution for ridge regression. So this is AT for ridge regression right here. It's the closest point, which means the smallest ball that touches this restricted area setting. So this is a solution that lies within a radius t L2 ball, but this is not a valid solution for the lasso. To get a valid solution for the lasso, I'm going to end up finding a solution here. I'm going to end up restricting to a slightly larger. My solution will have a little bit more. Oh gosh, okay, a little bit more air. There we go. So I'm going to have a little bit more air. So this solution right here, this is AT for lasso. Okay, so this will be the lasso solution, the closest point to A hat on this blue ball of radius t. It's an L1 ball, so it's this diamond-shaped thing. And the special thing about it is that it happened to be on this corner. Okay, when you get these pointy things which are restricted areas, your solutions, the closest points, are very often going to be on these corners. And this corner is exactly where this coordinate is 0. Okay, so that's where the sparsity comes from. You're going to you're restricting to these L1 balls, which have these very pointy shapes, but they're still convex, which is just the kind of inherently what's going to allow us to solve this. It's this convex shape, but very pointy, and so I'm going to tend to find solutions on these corners. Okay, so the corner corresponds with where most of the coordinates, or with at least one of the coordinates, is 0. Okay, and so when we're looking at this L1 ball in higher dimensions, it's harder to think about this, but it's going to kind of come out in the other direction from the board as well and have more corners. So my solution may not always, so where I'm up here, so it's coming out like this, and it's going to be another point here. So it may not always wind up if I wind up on one of these vertices, that means all of my coordinates except for one of them are going to be 0. So that's a pretty extreme case. But in between these corners, right, there's going to be these ridges that runs along here. And if you hit on this ridge, a line between two of the corners, that means that only two of the coordinates are non-zero. So in order to have all the coordinates be non-zero, which still might happen, you would have to have it so the solution was kind of pretty close. If my solution here was kind of along this direction here, then if I have any ball, the circle is probably going to hit somewhere here, and that's going to have all the coordinates be non-zero, and that's not going to give me sparsity. But that's saying that the true solution had about all the coordinates being the same value, so I couldn't really make up my mind. If one of the coordinates is more important than the other in the true solution, right? If I look at this solution here, I have this. If this was the least squares solution, the x value, the first direction, was much larger than the second direction. That means that one was much more important towards my goal. That coordinate was more important, so when I end up with this solution, I'm going to tend to pick that coordinate which is more important. And so this magically ends up giving me a solution that tends to be sparse but still relatively informative. What's going on here? Yeah.
You said that T is inverse proportional to S, but it looks like it's proportional because the one room should be just S times that times A, or the largest column.
So let's see. So if S is 0, okay, so if S is 0, that means I'm going to get the least squares solution. Yeah. And that means my restricted ball has to grow to include the solution. If I get a solution for S, for a value of S that's larger than 0, it's going to be biased towards being smaller. And so the larger S means more bias. The more bias means it corresponds to being restricted in a smaller space.
So shouldn't that be T equals AS for 1 over S or something like that?
Yeah, so this solution right here, if as S gets larger, this value is going to be smaller, the norm of this. The more, if I ramp this parameter up, I'm going to tend to bias towards an even smaller value for A. Right, so as A gets larger, I'm saying that, so if I said this whole term here could be at most 100, and I set A equals to 50, then this could be at most 2. If I set A equal to 5, then this could be 20. Right, so there's this inverse relationship. Yeah. Okay, so this is kind of why this is why sparsity works, right? This is why you get this sparsity part out of here. If I were to restrict to a zero norm, where I'm just counting the number of components, then there's a notion of like I can kind of think of taking like the zero dimensional or the zero norm, the L0 ball around zero, and it's going to get these really kind of weird pointy things. This is much harder to think about, but you can think of if I took instead of an L1 ball, I took like an L 0.1 ball, right? So something weird like that. Then I'm going to tend to get my restricted area is going to lie something like this. And so once I do this, it becomes, at a certain value, it gets impossible basically to get, well, no, it's not impossible to get. So like if A hat was in here, I could still find the closest point was here. It kind of becomes weird. I have to check these multiple directions. This is why it becomes harder if this becomes less than 1, because now this shape is not convex, and I can't just move towards the origin, or kind of I can't as easily find the closest point. So that could be weirder if it was less than this, and that still wouldn't necessarily give me something that's very sparse. But if I was outside here, it's going to almost impossible to have the closest point be on this line. It would have to be in here. So if A hat was out here, it'd be impossible for the closest point not to be this corner. Even if I was out here, it would hit the corners before it hit someplace inside. But I can't optimize that. When I have this L1 restriction, I can still optimize it, and it still tends to give a lot of sparsity. Okay, so it's kind of the picture of what's going on here. So it's kind of makes sense. All right, so how do we solve this? How do we find this point? Right, it looks like in this two-dimensional picture we can just kind of check all the corners, right? But in higher dimensions, it's not necessarily going to lie in the corner. It could lie on one of these ridges between two corners, or it probably does, right? If your solution has more than 2 values to it, it's going to lie on more than a ridge. It's these higher dimensional simplices, and it gets complicated to think about. So in higher dimensions, we can't really kind of check all possible locations of where it could be. It becomes kind of tricky, but we're going to do something like this orthogonal matching pursuit. Okay? We're going to do something like this, and the least angle regression is going to be like this orthogonal matching pursuit. Those are going to use some ideas from this shape. Okay, so try and okay. Okay, so we're going to start out the same way as we did before. So the idea here, the idea is let me kind of illustrate first, or I shouldn't try and draw anymore on the screen, but just explain it with the picture up here. So what we're going to try and do is we're going to try and gradually grow the value t and always maintain the optimal solution. Okay, if we start out with t equals to 0, this is essentially like setting s equal to infinity. And with t equals to 0, we know that the solution is going to be right here at the origin. It's setting all the coordinates to 0. Okay, and then when I let t be a little bit bigger, what do you think is going to happen when t gets a little bit bigger than 0? Yep.
Will you get a lot of solutions at the 4 points?
Yeah. So you have to keep in mind, in higher dimensions it's more complicated, but yeah, it turns out. So think of the larger I make s, the more sparsity I'm biasing towards, right? So that means the smaller I make t, if I make it all the way to 0, I get complete sparsity. It's all zeros. I said I'm just giving up. I'm going to say 0 is a good estimate. And I've seen some data sets where actually returning all zeros actually works reasonably well compared to some fancy machine learning algorithms. But so sometimes you give up, you say it's all 0. But if I make it a little bit bigger, it turns out unless you get some really strange cases, you're always going to get exactly 1 coordinate. You're going to get 1 value. So sparsity is going to go from 0 to 1. And as you increase t, you're going to get more and more coordinates that are allowed. Right? So if I increase this ball further out so it included the optimal solution, right? Then after that point, then I have all the coordinates, right? I have no zeros unless the optimal solution happened to lie on, in some spots where the coordinate was 0, right? So as I made it large enough, it's going to have all the coordinates. If I make t really small, it's going to have no coordinates. And as I make t a little bit bigger than 0, it's going to have exactly 1 coordinate.
So we're making the ball bigger in every direction. Right?
Correct.
So why wouldn't points in other coordinate
Right.
quadrants?
Okay, good. This gives me an excuse to redraw this picture here. Okay, so this is our basis again, and we'll draw this L2 ball. And so this is the value t here. But think t is really small, so probably the optimal solution is going to be out here, pretty far away. And if it's really far away, then only, even if you're in higher dimensions, there's going to be some corner which is going to be closer than the others, right? This corner is going to be closer. And how do we know which corner to pick? Which corner is going to be probably the closest? So we often don't start with this. What we start with is instead we'll think of starting with this y, and so y is going to be so y we can't completely solve with the linear equation. So you should think of y as actually the solution space is down here, but y is actually going to be coming out of the board a little bit. But we're doing an orthogonal decomposition, so we can think of the part we can't possibly capture is the part coming off the board. The part we could capture with our linear system is a hat. So y is out there, and we're trying to explain y as best we can. And so you're going to think of each of these directions. This is going to be x1, this is x2, and what we're going to do is we're going to say let j equals arg max of j of xj times y. Okay, so this is saying which of these directions is pointing most towards y. Right, so if you remember this dot product, so everyone remember kind of the geometric meaning of a dot product? The dot product, if I have this vector x1, I'm essentially thinking this kind of goes out here, and y I'm projecting onto here, and then this length from the origin is the norm of x1 y. The length of once I projected y onto this vector, the length from 0 is the dot product. If this was a unit vector. And if I have x2, well, I've got another vector here. I can project it onto here, and then this length, this is the norm of the dot product of x2y. Right? And so this one is much larger. Right? This one is going to be larger, so I picked j. This is going to be the first coordinate, because that's saying if I look at y, this first coordinate gives me a much better explanation of what's going on here. And so I'm picking y with the most explanation of what's going on. And it turns out when you start increasing t, this is going to be the first parameter that you pick. It's the first parameter that you want to set. Okay, so I want to pick this value j. And then the first step is basically going to be kind of, so this is like the first step in orthogonal matching pursuit, except the next step is not just to try and factor this out. I know what the solution is, right? The solution is easy. It's going to be exactly where it's t on the x1 coordinate and 0 elsewhere, right? It has to lie inside this ball, and I want to make it as close as possible, so I'm going to set exactly this value t. And then as t grows, I know exactly where it's going to go. As t gets a little bit bigger, it's going to keep, the next solution is going to be right here as well. And then if I keep growing t, right, I'm going to get, the solution is still going to be right along here. And then if instead of, let's move this guy over here, what's going to happen is that at some point, let's put it, say, right here. Okay? There we go. So let's set this be a hat. Get rid of this. Okay, so if a hat is right here, then there's this magical transition point where right at this location, where this is some value t, we'll call this t2. At this point, so up until when t was smaller, the closest point was here. At this point, the closest point, no, I didn't draw that quite right. Okay, let me try this again. I want to draw it so if I draw a ball like this, and I put, there we go, I put a hat here. At this point, the closest, if I use this value of t2, the closest point is still right on the corner. But if I make it any bit bigger, if I make this any bigger, now the closest solution is going to be right here. And now it has an x2 coordinate in addition to an x1 coordinate. So there's some magical point t2 where I start needing 2 coordinates instead of 1 coordinate. The best solution for that value t then involves x1 and x2. And there's some point where this happens. Okay? And so it turns out that everything going on here, because the value, the optimal solution, is growing at this rate which is linear, that I can actually solve for when this occurs. I can keep track of, so I can write down, so what I do is I write down, let's see, this RT. So this is the residual, what's left. And I can think of this residual either as sliding x out this way, or I'm sliding a back over this way. If I slid it over this way until it is exactly equal distance, or if it was exactly right until it was right here, then it would start using both of these coordinates. So I can think of this residual as y minus d of xj. Okay, and so these are my estimates of a. And so I know that when the value of t is here, then my estimate of a1 is equal to t. Right? So this is just some linear equation. And what I want to solve for is when the dot product of xj prime of r t, this norm, is equal to xj times r of t here, right? So this is the coordinate I picked the first time, and this is some other coordinate. And at some point, as I'm increasing this value, as I'm decreasing this residual, these are going to be equal. And when these are equal is exactly this location where you start using the second coordinate as well. And so but this is still going to be a linear equation even if I have more than one coordinate that's active. So I can keep increasing this t, and I can keep solving for when these critical points happen. Okay, and so at this point it starts getting kind of a little messy to describe this in more detail, but you can kind of see you can always maintain this optimal solution as you're growing t. And you have to detect these critical points where it becomes useful to start adding some of the to some of the value t. So you kind of have this quantity t that you're distributing onto these different coordinates, right? And so as you're distributing onto these coordinates, you're kind of doling it out at this linear rate, and the linear rate changes, and it's always linear, but it changes at these critical points where these things happen, where like it aligns right along this line here, or you can write this up as a linear equation. And so there's some algorithm you can write out to do this, and I kind of sketch this in more detail in the notes. There's this really great book by there's this book called The Elements of Statistical of Statistical Learning by Shibarani and Friedman, and they basically have a whole graduate level textbook about this topic where they describe this in much detail. I tried to summarize that into one kind of chapter of my notes. That might be a good first. So, and hopefully, if you're using this, there might be some packages you can use. Implementing this is a bit of a pain, but it can be done. Okay, so at this point, let's assume that I've magically described this kind of fairly tricky algorithm to you, and you all believe me that you can run this, right? If you're using this, do you just call this algorithm and run it, or is there anything left to do? Have we left any loose ends here? There are a couple things left we have to worry about. Okay, so one thing was we had to choose. So we solved this for every parameter t. Okay, so you keep running this, and you run this algorithm, you're growing this ball, and eventually you find the least squares solution, which you could have gotten just by doing this matrix inverse. Right, so what value, which solution do you return for A? So it turns out if you're maintaining these residuals and these values A, then what you can do is you can also, if your data was broken down into this training set and this test set, then as you're doing this, you can maintain the performance on the test set, right? Because you're linearly increasing this, the performance is actually going to be continuously deforming. And so you can maintain the score. And for every interval between these breakpoints, there's going to be one minimum value. And so you can keep track of these. And so you can find actually the single value of t, which corresponds with the single value of s, which gives you the best performance on your test set. So if you run this carefully, not only does it regularize, but it tells you which is the best value to actually use. Right? So it tells you the value of t as well. So you can, by running this, you can get that out. Okay, so that's kind of one last thing to do. There's one more problem with this algorithm. So this least angles regression problem was this one where you're growing this value t and you're maintaining these solutions. And you're always adding one coordinate at a time. But this unfortunately, this seems like a really cool algorithm. And you can do it in, I think it runs in like n squared time, because at each, in like t in n times d squared, because at every, you have at most d things, your d coordinates you're adding, and it takes n time to update each for the breakpoints and so forth. The problem is that this may not give the right solution, and the problem is you're again doing this greedy thing where you're adding a coordinate, and then once you choose it, you're kind of stuck with it. Okay, and that's not always the right thing to do. It could be that there are two coordinates, which there's one coordinate which worked pretty well, but there were two coordinates that together did a better job explaining than this one coordinate by itself. And it's a little hard to draw this picture because you need to at least be in three-dimensional space to see this. But sometimes you'll start out with one coordinate, and then later you want to set this coordinate to 0. You want to say, actually, I don't need this coordinate anymore. I'm going to snap that one back to 0. So what you do is you're growing this ball, and you can actually, if you look in this book, there are some nice illustrations where they track all the coordinates, and they're increasing and then decreasing. Sometimes the coordinate will start being positive, and then it goes, these coordinates can be negative as well, so sometimes they'll start positive, and then it moves towards negative. But when it moves from positive to negative, it's crossing over 0. And the point where it crosses over 0, sometimes, in fact, the optimal solution is often to leave it back at 0. And then only choose it again if it's the direction which is giving you as much influence as the other ones. And so you sometimes want to snap these coordinates to 0. It seems like, okay, so this algorithm was already kind of complicated, so doing that doesn't seem so bad. The problem is that you then may have an exponential number of steps. There are these weird constructions where you may want to have, at some point during the run of this, you have every possible subset of coordinates. So you end up getting an algorithm which is like n times 2 to the d to solve this properly. So I don't know of any way to solve this in polynomial in d time. So the actual best solution for this is actually, it may be exponential in d. It may actually be very hard. But in practice, that usually doesn't happen. So there's another form of this algorithm that's not least angles regression. It's like least angles absolute regression or something like that. And that snaps things to 0, and usually that doesn't run that much longer. But that actually gives you the optimal solution. So there's a couple of details in working this out. So if you've looked at the homework, you're going to have to do some regularized regression in the homework. But I promise you they wouldn't be too hard, so I'm going to only have you do it so just using the ridge regression, which again had a simpler solution. But if you're able to kind of do this in practice and you can get software packages that will run this for you, then you should try running this. This will give a more robust and a sparser solution, which will probably generalize better. It means it gets rid of the unneeded coordinates in kind of in the optimal way and under this sense of optimal. So it's pretty cool. All right, so next week we'll talk about noise in general and cross-validation, and there'll be a lecture on privacy of data and talk a little bit about the ethics of doing doing this sort of mining on data. It's kind of an emerging area of importance, or something people would like to ignore, but we'll have to talk about it. So.
So I think I understand